it turned blue. On October 29, 2025, the interstellar visitor 3I/Atlas hit perihelion, and instead of glowing the usual comet red, it erupted in a piercing blue, as if burning hotter than the sun's surface. Solar coronagraphs confirmed the impossible. The color shift defied fundamental physics, raising the stakes far beyond any comet mystery on record. Could 3I/Atlas be our first real evidence of new physics or even technology? Here's how the data forces us to confront the limits of what's natural. By October 21st, it reached conjunction, passing almost directly behind the solar disk. For ground-based telescopes, the window slammed shut. No optical or radio observatory on Earth could track the object during the most critical phase. Its perihelion passage on October 29th, when it would graze just 1.36 astronomical units from the Sun inside the orbit of Mars. The task of monitoring 3I/Atlas during this invisible interval fell to a specialized network of space-based solar observatories. 3 platforms form the backbone of this campaign. SOHO, stationed at the Earth-Sun L1 point, kept a continuous coronagraphic watch on the near-Sun environment. Stereo, A, leading Earth by more than 20 degrees in its orbit, provided a crucial off-angle view, allowing scientists to peer around the edge of the Sun from a different vantage. GOE-19, launched in 2024, and equipped with the CCOR-1 coronagraph, contributed high-cadence imaging and multispectral coverage during the brief period when its geometry permitted a clear line of sight. Each instrument brought unique strengths. SOHO's LASCO suite delivered broadband white light imaging and polarization data essential for mapping the comet's evolving envelope. Stereo A's COR-2 instrument offered a complementary angle, ensuring that the object could be tracked even as it slipped behind the Sun from Earth's perspective. GOE-19's CCR-1, with its advanced color photometry and rapid exposure cycles, captured subtle changes in the object's brightness and morphology at perihelion. From October 21st through early November, these 3 observatories maintained overlapping coverage, synchronizing their clocks and calibrating cross-instrument readings to ensure no detail was lost. Data gaps were minimal, just a few hours lost to telemetry resets or brief pointing adjustments. The resulting dataset provided an unbroken record of 3I/Atlas's behavior during its most inaccessible phase. It is from this vantage, locked in space and time, triangulated by 3 solar sentinels, that the story of the perihelion anomaly unfolds. No natural comet or asteroid in the inner solar system has ever displayed blue-dominant emission near the Sun. To understand why, it helps to look at the physics that governs how objects absorb and emit light. The color of thermal radiation depends on temperature, described by Wien's law. The hotter the object, the shorter the wavelength of its peak emission. For most familiar bodies, planets, moons, even active comets, this means their brightest thermal glow sits deep in the infrared. The Sun's own surface, at about 5,800 Kelvin, peaks in visible light close to yellow. For an object to appear blue by its own heat, its temperature would need to rise above 6,000 Kelvin, well beyond anything observed on a comet or asteroid. 3I/Atlas reached perihelion at 1.36 astronomical units from the Sun, just inside Mars's orbit. At that distance, the solar constant is about 770 watts per square meter. That's the maximum energy available to heat any passive surface, no matter how dark, how reflective, or how exotic its makeup. Even if every bit of sunlight was absorbed and instantly re-radiated, the equilibrium temperature for a typical comet nucleus or dust grain would remain far below 500 Kelvin. That's barely enough to make water boil, not enough to shift visible light toward blue. Standard models predict a redder glow as dust and gas scatter sunlight and radiate away absorbed heat, mostly in the infrared. The observed blue shift at perihelion, confirmed by independent instruments on SOHO, Stereo A, and GO-19, stands in stark contrast to these expectations. The color transition was not subtle. Photometry shows a clear dominance of blue wavelengths, with emission peaking near 450 nanometers. According to black body theory, matching that color would require a temperature on par with the solar photosphere itself. No known comet, regardless of its orbit or composition, has ever come close to this regime. Even the most active Oort cloud comets, which can flare dramatically as they approach the Sun, remain hundreds of degrees cooler and display spectra shaped by reflected sunlight and discrete emission bands from gases like cyanogen and diatomic carbon. Attempts to explain the blue emission through conventional mechanisms such as shock heating, meteoroid impacts, or rare chemical reactions fall short. Localized hotspots might briefly reach higher temperatures, but there is no evidence for the kind of sustained, spatially extended heating that would be needed to produce a blue-dominant envelope hundreds of thousands of kilometers across. Nor do the data show the strong infrared excess that would accompany such an event. The absence of these signatures, combined with the sheer scale of the blue emission, rules out passive thermal processes as the source. This leaves a fundamental problem. Under the laws of physics, as currently understood, no inert body at 1.36 astronomical units with only solar input should emit such intense blue light. The thermal budget is simply too small, and the required temperatures are out of reach. Any explanation must account for this constraint before considering more exotic possibilities. The blue at perihelion is not just surprising, it is physically extraordinary, demanding a closer look at what could make an interstellar object defy the established thermal limits. August imaging of 3I/Atlas captured a familiar sight. A faint green-tinted envelope stretching tens of thousands of kilometers from the nucleus. This color, seen in comets across the solar system, comes from diatomic carbon and cyanogen molecules that fluoresce under sunlight, painting the coma green as the object sheds gas and dust. Phototrick records from SOHO Stereo A and GO19 agreed on this baseline. But as October drew to a close, the object's profile began to change in ways no cometry model could anticipate. On October 29th at perihelion, the color profile underwent a sudden and dramatic transformation. Calibrated photometry from all three coronagraphs, cross-checked against each other and against their own historical data, showed the green emission falling away, replaced by a deep, broadband blue. The shift was not subtle. The emission peak moved to around 450 nanometers, a wavelength associated with objects thousands of degrees hotter than any known comet. The data chain was robust, with synchronized timing and independent calibrations, ruling out instrument error or solar background contamination. At the same moment, a second anomaly became apparent. The luminous sheath surrounding 3-Atlas ballooned in size, expanding to nearly 300,000 kilometers across, about a quarter of the sun's diameter. This envelope was not a faint haze, but a sharply defined shell, brighter and more coherent than anything observed from Oort-Cloud comets, even during their most violent outbursts. The rate of brightening measured in the days leading up to and just after perihelion far outpaced the standard dust-driven models. Instead of following the expected curve where brightness climbs gradually as the object nears the sun and then fades post-perihelion, 3I/Atlas surged in luminosity, reaching a peak that rivaled much larger, more massive comets. Instrument teams traced the envelope's growth to a discrete event in August, when all three platforms detected a sudden spike in carbon dioxide emission. This CO2 plume, brief but intense, coincided with the earliest signs of the color shift. The gas signature faded within days, but the expanding sheath and blue emission only intensified as perihelion approached. Attempts to model the light curve using known mechanisms, sublimation, fragmentation, even energetic outbursts, could not reproduce the observed brightness or the scale of the envelope. The thermal budget at 1.36 astronomical units simply did not allow for this level of activity, especially not in the blue. The direct conflict between observation and model left little room for conventional explanations. The evidence stacked across three independent instruments pointed to a process beyond the reach of solar heating and ordinary cometary physics. The green to blue transition, the explosive growth of the luminous sheath, and the nonlinear surge in brightness all defied expectations. For astronomers accustomed to the predictable choreography of comet behavior, the data from 3-Atlas brought not just surprise, but a fundamental sense of disquiet. The catalog of anomalies was only beginning to take shape. A full accounting of 3-Atlas's irregularities begins with its path. The object entered the solar system on a trajectory pinned to within 5 degrees of the ecliptic, an orientation so flat it defies the odds for an interstellar arrival. Most known visitors from beyond the sun's reach cut through at steep angles, reflecting the random tilt of their home systems. Yet 3I/Atlas threaded almost exactly along the plane where planets orbit, a statistical outlier that immediately drew attention from orbital dynamicists. The next anomaly surfaced in the behavior of material ejected from the object. Standard cometary activity, driven by sunlight heating the nucleus, sends gas and dust streaming away from the sun, forming long sun anti-Ward tails. In contrast, coronagraph images captured repeated episodes of material blowing sunward directly toward the solar glare. This reversal is not just rare. It is fundamentally at odds with the physics of volatile sublimation and solar wind pressure. No known comet in recorded history has shown persistent sunward ejection at this scale or distance. Spectroscopic analysis deepened the puzzle. Across multiple observing platforms, the ratio of nickel to iron in the ejected dust was found to be unusually high. In typical solar system comets, iron dominates, reflecting primordial solar nebula chemistry. Here, nickel appeared in near par excess compared to iron, a signature more reminiscent of engineered alloys than of naturally formed rock or ice. Laboratories handling these measurements have repeatedly cross-checked calibration files and chain of custody logs. Yet, the result holds 3I/Atlas's dust is chemically distinct, with a metallic fingerprint that resists easy classification. The object's incoming vector brought another coincidence. When plotted against the sky, its approach aligns within a narrow window of the constellation Sagittarius, close to the coordinates of the 1977 WOW signal, a famous one-off radio burst that has fueled STI speculation for decades. While most astronomers caution against reading too much into this overlap, the spatial coincidence has not gone unnoticed in the anomaly ledger. Compositional analysis from both photometry and mass estimates revealed yet another departure from the norm. Water, the dominant ice in nearly all comets, accounts for only about 4% of 3/Atlas's volatile content by mass. In contrast, typical comets carry water fractions of 80 to 90%. The remainder in this case is made up of carbon monoxide, carbon dioxide, and other rare volatiles. Again, an unusual mix for any known solar system body. Each of these findings, low inclination approach, sunward ejection, high nickel to iron ratio, sky alignment with the WOW signal, and a water pore composition, stands as a discrete, independently verified anomaly. None alone is definitive, but together they form a ledger of irregularities that strains the bounds of natural cometry physics. The evidence is cataloged, cross-checked, and ready for the next stage, a rigorous audit of data integrity and the search for systematic error before any further conclusions are drawn. Avibe, a Harvard astrophysicist known for his risk-weighted approach to cosmic anomalies, added 3/Atlas's Perihelion event as the 10th entry in his ongoing catalog. After reviewing the blue emission data and the full anomaly ledger, Lowe revised his estimate for a technological origin to slightly above 4 out of 10. Higher than for any previous interstellar visitor, but still short of outright endorsement. He notes that if the blue shift is confirmed as intrinsic emission, not a sensor or solar artifact, it would stand outside the boundaries of current comet physics. 4. Loeb, and a growing number of researchers, the pattern of irregularities, low inclination entry, sunward ejection, engineered alloy signatures, now warrants an open probabilistic discussion of all options, including artificial power or thermal management. The debate over interpretation, however, is matched by tension over access. On October 2, 2025, GOE-19's Sigma Year sensor captured a packet of high-resolution multispectral images as 3I/Atlas neared perihelion. The data, with effective resolution down to 1.2 arcseconds and coverage across 12 spectral bands, was immediately classified. Intelligence agencies cited concerns over sensor calibration and national technical means, while scientific advocates argued that only open, independent analysis could resolve the blue emission's true nature. Representative Ela McAdams, serving on the House Science, Space and Technology Committee, has led the push for declassification, framing the issue as a test of public trust in science. Meanwhile, outside formal channels, amateur astronomers and citizen scientists have pulled observations through the Minor Planet Center and informal networks, but without a unified campaign or institutional oversight. Their contributions, while decentralized, add to the growing call for transparency and independent replication. As the scientific community weighs the odds and the public demands access, the standoff between secrecy and scrutiny has become as much a part of the 3EY/Atlas story as the object's own unexplained behavior. Three competing ideas now define the 3/Atlas controversy. One proposes an unknown natural process, perhaps a new class of volatiles, or an unexpected photochemical reaction behind its blue glow and unusual activity. Another sees 3I/Atlas as a rare statistical outlier, a natural object whose oddities require no new physics. The third, once dismissed but now under careful scrutiny, suggests technological origins, engineered materials, active heat management, or even deliberate energy output. To resolve these questions, astronomers have set strict falsifiable criteria for the next observational campaign. On December 19, 2025, as 3I/Atlas nears Earth, both the James Webb Space Telescope and the Hubble Space Telescope will observe it at close range. Their coordinated effort will gather four types of data: high signal-to-noise spectra from ultraviolet to mid-infrared, searching for structured emission lines or telltale slopes; imaging polarimetry to measure polarization angles and degrees across the coma, key for distinguishing exotic dust from engineered surfaces; precision astrometry, tracking the object's path for any non-gravitational or controlled motion; and mid-infrared mapping, looking for heat signatures unexplained by sunlight. Decisive outcomes rest on these benchmarks: organized radio signals, clear excess infrared emission, or abrupt non-random trajectory shifts would support a technological explanation. Natural spectral bands, polarization matching plausible dust, or no infrared excess would favor a natural origin. For the first time, citizen scientists worldwide are joining professional teams sharing phototrick, astrometric, and radio data in real time. The coming months will reveal whether 3I/Atlas forces a rewrite of comet science, or stands as the first interstellar object to raise testable evidence for artificial origin. On October 29, 2025, three independent solar observatories, SOHO, Stereo AA, and GO19, recorded 3/Atlas turning intensely blue at Perihelion, a shift never before documented in any natural body at this distance from the Sun. The object's color transition, luminous envelope stretching over 300,000 kilometers, and unique nickel-to-iron ratio challenge established comet models. Key anomalies, including a low water content of just 4% and sunwood material ejection, remain unexplained. As of today, high-resolution images from October 2nd are still classified, and no structured radio signals or infrared propulsion signatures have been detected. With the next observation window set for December 19, 2025, using JWST and Hubble, the central question persists. Does 3I/Atlas represent unknown natural physics, a rare cosmic outlier, or evidence of technology? The answer will depend on data yet to come. For now, 3I/Atlas stands as the most anomalous interstellar object ever observed, reshaping how the scientific community prepares for the next visitor from beyond our solar system.